Ladies and gentlemen, welcome to the lecture number 10 in Calculus 1. Well, finally this time we will start talking about derivatives. And well, before I go into and diving into the subject, let me tell you about the pictures you can see behind me. This is the Cathedral of Learning. This is, well, in the campus of University of Pittsburgh. It's one of the tallest buildings in university campuses. I think it's the fourth one. It's a very nice. It's a copy of the Cathedral of Notre Dame from Paris. Anyway, let's get started. Like I said, we'll be starting talking about derivatives, and I'm not gonna go and talk about the rules yet. I just want to start with some basic stuff about derivatives. So first one I would like to talk about, so an introduction to the derivatives. And what I would like to talk about is tangents. Okay. All right, so well, let me talk. Well, I think I've talked about this a bit in the first lecture when I talked about the tangent, slope of a straight line, the slope of a tangent. I didn't say exactly what the derivative is, but I mimicked it. So now let's start slowly, and we will say a few words about the slope of a straight line. Okay. So the slope of a straight line, let me draw a picture first. And so let me just draw it like this. So this is the XY axis, right? And now what I'm going to do is I'm just going to draw a line. So imagine that this is a line, right? And we can write this in slope-intercept form, but let's just say we have some points. Let's say we have here A, B, and here we have something like, so this will be a point on the line. So here will be f of A, and let's just say here we have B, and again this will be a point on a line. Ooch. So it will be here. This will be f of B. Okay, and let's just say, so this line, right? And let's just say here we have two other points, for example, C and D, and this will be here. So we'll have f of C here, f of D here. So they will intersect. There will be these 2 points right here on the line, right? So this will be the line, the equation of the line in slope-intercept form will be mx plus b, right? As you can see it, right? Okay. Now, well, here m, you know that this will be the slope. And you know that the expression for m, so we can write it here, is nothing else than just f of c minus f of d over c minus d. Or it doesn't matter which point you take on that line, the slope will be the same. Or you can write this as f of b minus f of a over b minus a, right? So it doesn't really matter. So you can consider other 2 points, and then you can take this difference, and it will be the same. So we can say that, so let me point out this remark. Well, for a straight line, because this is important, for a straight line, the slope is the same right for the entire time. So keep this in mind. This is a very, very important observation. So this is what happens in the case of a straight line. Now, so this is the story with the slope of a straight line. Now let's see what happens when we would like to talk about the slope of a curve at a point. So the slope of a curve at a point. All right, let's just draw again the axis. And let's just say we have some function that goes like this. And here we have a point P. And here we have a tangent to P, right? As you can see here, that's a line. It's a straight line. That's, in fact, let me draw it. Oops, sorry about that. Okay, and let me draw this straight line. Okay, again. So this is a straight line, which is tangent at this point P. So we say that this guy here, so this is a tangent line at the point P, right? As you can see, it's tangent to that curve at this point. Well, this tangent line, I want to make myself clear from the beginning. So the tangent line at a curve is a straight line. This is important. So it's a straight line that touches the curve right at the point, at only one point P, as you can see here. So there is no way you can draw other tangents to that curve at that point P. So it's at only one point. All right. Now in this case, we can say that the slope of the curve, so we can say that the slope of the curve at the point P is the same as the slope of the tangent line, so the same with the slope of the tangent line at the point P. So, and now this will become very important for our future purpose, because we will try to relate the derivative in terms of this. And now I would like to say one more thing, to point out just a small remark, that is that the tangent line represents instantaneous rate of change right? So this would represent the instantaneous rate of change of the function at one point. Okay, so we have this. So at this point, we don't know what the derivative is, but somehow keep in mind this slope of the tangent line at that point. Now I would like to, so we have seen what it is, the slope of a curve at a point. Now I would like to talk about the slope of a curve. So another thing that I would like to talk about is the slope of a curve. Okay. All right, so let's draw a picture again. So suppose that we have a curve like this. And now what I'm going to do is I'm just going to draw some tangents here. Ouch, not this one. Oops, sorry about that. This is the curve. Okay, and now I'm going to draw some tangents here. Okay, let me draw one here. Oh my. One here, okay. Let me draw another one here. Let me draw some other ones here at the point, maybe some other one here, and so on, right? So we can draw tangents that touch at this, at one point, let's say. All right, so we can say that the slope is defined, this is an important thing, and I would like to mention this. The slope is defined at every point along the curve. So that's very important to know. This is what we should keep in mind about, well, the picture is quite unfortunate, but anyway. Okay, now we can say that the slope is changing the entire time. Right? Well, in other words, we can say that the slope of the curve depends on what point you choose on the curve. What point you choose on the curve. So this is how we can interpret this this picture, right? All right, so this is the story with the slope of a curve. Now I want to talk about a bit about the secant line. So let's see, what can we say about the secant line? All right, so the secant line, again, let me draw a picture, all right? Maybe the picture, okay, now let me draw it here. These are the axes, X, Y, Z. And let's just say we have something that goes like this, right? This is, I have these points P and Q here, right? And so this is what we call the secant line. This is the secant line. Right? So you take 2 points on the curve, right? Then you just draw the line. So that's what we call the secant line. So let's just write it. So we say that a secant line is a straight line right? Joining 2 points on the curve. All right, so that's what we know, right, about the secant line, as you can see in the picture. And now the slope of a secant line, we can say something about the slope. So the slope of a secant line is nothing else, is the average rate of changes. That's what average, in fact, let me write it in this way, is the average rate of change. That's what we need to know about the slope of the secant line. So is the average rate of change between these 2 points, between the points, so 2 points P and Q. Okay. Now, we would like to address the following question. How do we find how do we find a slope at a point, or maybe this, the slope at a point on the curve? So that's the big question we would like to address first. And again, let me draw a picture, and probably this picture will be a little bit familiar if you watched closely the first lecture, because I think I did this. But anyway, let me draw it again. So again, we have the axis, x, y. And now let me draw something like this. So this will be our function. So this is the graph of our function. Okay, and now what we would like to do, we'll have P and Q, right? Let's say we have 2 points here. So let's say we have here x0, and let's just say here we have, okay, let me, this is x0 plus some difference, delta x will denote this, right? And here we will have f of x naught, right? And here we will have, let's just say f of x naught plus delta x, right? Okay. All right, so we have this picture. Now let me just draw the secant line between, so this is the secant line. So let's keep this in mind. Right, so this is the secant line. And now the difference here, if you look at this, between these two is nothing else than just delta x. Okay, so this is the picture, and we would like to interpret this picture a bit. And using this picture, we would like to answer the question. So how do we find the slope at a point? So this is the very what I'm interested in on the curve. So on our curve. All right. The procedure is the following. So step one. We need 2 points to find the slope, right? So choose, so we need 2 points to find a slope. So we choose another point on the graph. Let's just say Q. Let's say Q. Okay, so we have P and Q. Look at the graph. And now step 2. The slope between P and Q, between these 2 points, P and Q, is the slope of the secant line joining P and Q. So joining these 2 points, right? P and Q. And we'll denote this guy, I'm going to write it in the following way: delta y over delta x. And this will be nothing else than just f of x naught plus delta x minus f of x naught over x naught plus delta x minus x naught. But this guy, if we do a little bit more algebra, is nothing else than just f of x naught plus delta x minus f of x naught, everything over delta x. So this is what we need to know. Okay. Right? All right, step 3. Well, the question is now, we would like to, and this way we will go, we will delve more and you'll see what the derivative is. So I'm approaching that. So step 3, we would like to address this question. What happens, so I'm getting closer to the derivative. What happens when this guy, this difference, delta x, approaches 0? That is the question. And in fact, that's a very important question. Let me draw a picture again. XY axis. And let's just say that my curve is like this. Now let's just say I have here my point P. This is where my point Q is. Right? Okay. Let's just say here I have some, and I can have more points here. Let's say here. So here it will be x naught. Let's just say here I have x naught plus delta x. So the difference between these will be delta x, right? So let's point this here. But if I consider some other points here, let's just say some other points right here or even here. Right, or I can even point, let's say I'm taking one here. I'm also considering the difference between this guy and this guy here, right? Or this guy and this guy here. Or even from this guy to this guy here, right? So in other words, I want to see what happens as, let me draw this secant line here between P and Q. Between these 2 points, as I would like to see what happens as delta x will be very, very small. In other words, as P approaches Q, I want to see what happens. So, because this is a question where we like to see, we would like to see what happens when this guy is very small, basically approaches 0. As you can see, it's getting closer, but also the point Q, well, the distance between these 2 points is getting closer and closer. All right. So now we can say that by letting delta x to approach 0, right, we can bring the secant line, right, closer to the tangent line. So that's what we want. We want the secant line closer to the tangent line. That's what we want, right? Anyway, as this happens, right, the slope of the secant line right should approach the slope of the tangent line at the point P. At the point P. This is important. All right. So, and now we would like to see this. We would like to see what happens when we have this here. Okay, let's go further. So let's talk about the slope of a line tangent to the graph at a point. So let's address this. Okay. So at the point P of coordinates, let's say x naught and f of x naught. So right, we have this point on the graph of the function. The tangent line to the graph right? Graph of the function f of f. So the tangent line to the graph of our function f has the slope given by the following formula. And the formula is the following. So the slope of the tangent line, so I'm going to denote it like this, m tangent. And this will be nothing else than just the limit as delta x approaches 0 of f of x squared plus delta x minus f of x naught, everything over delta x. That's the slope of the tangent line. Well, provided that this limit actually exists. So let's mention that, provided that the limit exists. Well, guess what? If you look at this formula, the slope of the tangent line is nothing else than just what you are about to see in this lecture is nothing else than just the derivative at that point, x naught. All right, so let's not mention it yet. So let's just let me give you an example, and then we'll say explicitly what the derivative actually is. But I would like you to look at this formula. So the slope of the tangent line, keep in mind that is defined by this formula, is the limit as delta x approaches 0 of f of x naught plus delta x minus f of x naught, everything over delta x. And probably you have seen this in the first or second lecture when we talked about the difference quotient. So as you can see here, the quantity inside that limit is nothing else than just the difference quotient. Anyway, let's do the following example, a quick example. Let's just say, let's find the slope. So find the slope of the tangent line to the graph of, let's just say, let's take the simplest quadratic function, f of x equals x squared, at the point, let's say, p of coordinates -1, 1. So I will be interested in this. Well, this is plain and simple. It's quite clear what we have to do is just to plug in the numbers into the above formula. So so we have that the slope of the tangent line. Okay, I'm gonna at some point I will abbreviate tangent just M10 so that I don't need to write it, the word tangent over and over again. So by the formula, this is nothing else than just the limit as delta x approaches 0 of f of x naught, which in our case is -1, plus delta x minus f of -1. And here we'll have delta x. Right? Keep in mind that that point P of coordinates -1 and 1 is on the graph of our function f of x equals x squared. Why? Why is that? Well, simple, because f of -1 will give you 1. So -1, everything squared is just 1. Okay. So that's the formula, as you can see above even. And now let's just proceed and do the computations. So this would be equal to, so let's get going. Let's keep going. So this will be the limit as delta x approaches 0 of, well, my function is f of x equals x squared. So this will be -1 plus delta x, everything squared, minus f of -1. Okay. So this will be -1, right? And everything over delta x. Okay, and we can expand this. So we will use some basic college algebra knowledge now, which I hope you all of you will master this. So you can expand the binomial there. So this would be 1 plus, minus. So it's 1 minus 2 delta x plus delta x squared minus 1, everything over delta x. And this will give us lim as delta x approaches 0 of, so 1 here, as you can see, goes away. So I'll have only delta x squared minus 2 delta x, everything over delta x. And this is the lim as delta x approaches 0 of, well, we can factor something here. Delta x is delta x minus 2, everything over delta x. Again, we can simplify here again. And this will be nothing else. If we plug it in, this will give us negative 2. And that's it. This is how we find the slope of a tangent line at a point, right? Okay. Now, okay, now let's do another example. Let's just say example 2. So this was example 1. Okay. So the second example, let's see, we would like to find the equation of a line that is perpendicular to the tangent line. Okay, so find the equation of the line that is perpendicular to the tangent line to the function f of x is 1 over x at x equals 2 and intersects at the point of tendency. And let's see, what do we mean by that? So let's see this. So let's read the statement again. And all right, so the slope of a tangent line at x equals 2 is nothing else. So we have seen is, well, what we will call the derivative. So this would be basically, so this, well, if we do all this again, I'm just going to say it directly, is negative 1/4. And I'll leave this to you as an exercise to figure it out why. So the slope of the tangent line at x equals 2 is negative 1/4. So you just do the same thing as you did here. But this time, this will be for this function at this point. Keep that in mind. So you have to compute again the difference quotient. So you take the lim as delta x approaches 0 of f of x plus delta x, f of x naught, and in your case x naught is 2, so it's f of 2 plus delta x minus f of 2 over delta x. You plug it in and you will see that it's negative 1/4. Okay. So I'll leave this to you as an exercise to do it. And now we know that, keep in mind that the slope of that this line is perpendicular. We have this information here. is perpendicular to the tangent line. So we know the slope of this tangent line, we can compute it. And we know that the slope of the line that is perpendicular to the tangent line, well, you know something about those slopes. So we know that the product of those two slopes is -1. So so this implies that the slope of the line that is perpendicular that is perpendicular to the tangent line is what? We know that the product of two slopes is -1, but one slope is -1/4, so this other slope, it will be 4. Right? Keep that in mind. So let me mention this fact here. The product of the slopes of two perpendicular lines is -1. So keep that in mind. Okay. Now the equation of the perpendicular line. So the equation of the perpendicular line is given by y is 4x plus b. So we write this in slope-intercept form, right? Okay, great. Now we know that this line passes through the point of tendency. So this implies that x equals 2, and so f of 2 is 1/2. So we have that the point of coordinates, let's say 2 and 1/2. So we need to find b now. So keep in mind that we don't know b. We will use the tendency point. So using the tendency point, we have that 1/2 is nothing other than just 4 times 2 plus b. And from here it follows immediately that b is -15/2. So therefore, the equation of the perpendicular line is given by y equals 4x minus 15/2. Right? So that's what we wanted, right? We wanted to find the equation of the perpendicular line, and that's it. Right? Okay, now let me draw a picture so that you can see things better. So a picture. Oops. Okay, now what we're, so remember that we have this function 1/x. Okay, so let's just say that we have this, well, maybe the picture is not quite accurate. Let me do it again. Okay, maybe like this. So I have the point, let's say here 2, and let's just say here it's 1/2. All right. So this function, and it will be like this, right? And also it will be something like this, right? Okay, so this is how the graph would look like. And now we have this, what we will call the normal line. But anyway, it will be something like this. Which is given by this equation. So it's 4x minus 15/2, right? This is what we got here. Look at it. 4x minus 15/2. Okay. And we also have the tangent line. Let me draw it with, which is tangent to this curve. So let me draw it in this way. Ouch. Nah. Okay. Sorry about that. Okay. Okay. Now let me draw the tangent line, which goes something like this. Okay. So this is the, let's just say this is the normal line, right? And this guy here is the tangent line at x equals 2. So keep in mind, so this is the tangent line at the point x equals 2. And this tangent line has the equation. We know that this is -1/4 x plus 1. And this is the graph of this function. Let's just say here y equals 1/x. So as you can see here, they intersect, and moreover, they form what a right angle here. So they're perpendicular, right? Which means that the product of their slopes is a -1. Okay, now this is what we call the normal line. And now let's just say formally what it is. So I think you can see in the picture. I think it's everything clear from the picture. Even if you look at the slopes, right? The slope of the normal line is 4, and the slope of the tangent line at the point x equals 2 is -1/4. And if you take the product of these two, it will give you -1, which is exactly what we want to happen when two lines are perpendicular. Okay, now let's just say a few words about the normal line to a graph. So the normal line to a graph. Right? So the normal line to the graph of f, right, of a function f at the point P is the line perpendicular to the tangent line, to the graph at P, at the point P, right? So that's what it is. And now let's just draw a picture so that it's even clearer. So these are the axes. As you can see, I draw a lot of pictures because I want things to be even clearer. I want you to visualize things, not just to write like formally everything without you visualizing what's going on, because you need to have this geometric intuition about the derivative first of all. So that's what I want to tell you, is that is the slope of the tangent line. So that's what you have to keep in mind. So let's just draw a picture. So let's just say we have a function that looks like this. Okay, so this is the graph of f, let's say. And now let's just say I have this tangent line. Let me draw the tangent line first. So this would be something like this. This is the tangent line. And let's just say here I have the point P. So this is my point P. And we say that this guy here is the tangent line at the point P, right? And now I'm going to draw the normal line that will pass through P. In fact, let me just give you, this is my point P. And now I'm going to draw the normal line which will pass through P. It will be perpendicular, so it goes like this. So this will be what we'll call the normal line at P. So as you can see here, these two are perpendicular. So that's what you need to know about the normal line. So keep in mind this picture, right? So in other words, the slopes, the product of the slopes, it has to be is equal to -1. All right, and now finally, after saying all these things about the slopes of the tangent, the slope of the secant, whatever, normal lines, it's finally it's time to define the derivative, to say exactly what it is. So finally, we can say a few things about the derivative. In fact, we talked about it, but I didn't say explicitly what the derivative is. And now I'm going to say it. So the limit of the difference quotient and, well, this difference quotient that we've been talking about for the entire lecture. Let me just write it again. Is this limit as delta x approaches 0 of f of x plus, sorry, x naught plus delta x minus f of x naught, everything over delta x. Well, the limit of this difference quotient gives a formula for the slope of the tangent line to the graph of f. Right? For the slope of the tangent line to the graph of f. At the point x f of x, right? And it is called nothing else than just the derivative of f. It's called the derivative of f at x naught, and it is denoted by, we will write it in this way, f prime of x. Well, sometimes we have this notation, but sometimes we can write it in this way, the derivative of f with respect to x. The physicists prefer the second notation, so it doesn't really matter which way. You will see that in this course we will use both notations, so it doesn't really matter that much. Oh, so this is I want you to look at the definition. So just like I said, you need to take care of this guy. So we can write this guy as f prime of x at x naught, right? Okay, now let's see. Well, I would like to mention two things before we do some examples. So let me point out the following remarks. So the first one is that if the limit for the of the difference quotient right exists, then we say that the function f is differentiable at the point at x, let's say, right, f of x. Also, the second remark I want to point out is that the derivative of the function is itself a function. So the derivative of a function is itself a function. Okay, now let's see an example. Example number, I forgot the number anyway, I'm not going to number them again. So, and let's just take not the very simple function, let's take a little bit more complicated. So find the derivative of f of x equals square root of x using the definition. Okay, so we have this function, so we want to find the derivative using the definition. Okay, let's look back at the definition. What does it say? Look at it. You see, it's nothing else than just the limit of the difference quotient. So that's what we have to do. So by the definition, f prime of x is the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. So that's the definition. And now we just have to plug it in for our function, which is the square root of x. So this will be nothing else than square root of x plus delta x minus square root of x, everything over delta x. Oh, what are we doing here? Well, so how should we proceed further with this radical here? As you can see, we have a radical at the top. But remember in the last lecture, when we did those problems with limits and continuity, and at some point we computed the limit of some radicals, right? And those radicals were at the top, right? We did something. And what was that something that we did? Well, It's what we call the conjugate. So we multiply by the conjugate. So we multiply by the conjugate. The conjugate of this guy will be the square root of x plus delta x plus square root of x. So this is the conjugate. Right? Oh, you always do this. Okay. And now this guy will be nothing. Oh my goodness, I forgot to put the limit here. Sorry about that. So this is the lim as delta x approaches 0, right? F. And this guy will be equal to the lim as delta x approaches 0 of. Now let's multiply these. So it's the square root of x plus delta x minus square root of x times the square root of x plus delta x plus square root of x, right? The conjugate over delta x times the square root of x plus delta x plus the square root of x, right? Okay, so we have this. So let's keep going with our computations. So this would be equal to the lim as delta x approaches 0 of. When you multiply these guys, it will give us nothing else than just x plus delta x minus x, everything over delta x times x plus delta x plus square root of x. Okay. Which is, if we do more algebra, so as you can see here, x will go away. This is nothing else than just the lim as delta x approaches 0 of delta x over delta x times x plus delta x plus square root of x. Now, these two will go away, and this finally will give us the lim of delta x approaches 0 of 1 over the square root of x plus delta x plus square root of x. And now, as delta x approaches 0, so keep in mind that this guy here, so this guy here will approach 0. So once we do this, guess what? It will follow what? It will follow that this limit will be nothing else than just equal to 1 over square root of x plus 0 plus square root of x, which is nothing else than just 1 over 2 square root of x. So this is actually the derivative. So in this way, we found the derivative of our function of this function. So we can say that the derivative, so f prime of x, so if f of x is the square root of x, then f prime of x is nothing other than just 1 over 2 square root of x. Wow, you see? We use a definition to find the derivative of a function. And I would like you to play with other functions as well. For example, x squared. So the derivative of x squared. So other functions. For example, f of x equals x squared. It will give you that the derivative is 2x, and so on. So try to play around. So, or for example, you can consider the function x to the power n. So you will see that the derivative will be n times x to the power n minus 1. So this is how you play around with derivatives. And now let me give you a theorem which will tell us a bit more about the equation of a line which is tangent to a curve at a point. So theorem. So if f is differentiable. When I say differentiable, I mean we can actually compute the derivative. Is a differentiable function at a point, let's say x naught, right? Then the graph of y equals f of x, right? The graph of y equals f of x has a tangent line right at the point p of coordinates x naught f of x naught with slope, and the slope, guess what? It will be nothing else than just oh, sorry about that, with slope f prime of x naught. So it will be nothing else than just the derivative of f at that point. And equation, so the equation will be given by y equals f prime of x naught times x minus x naught plus f of x naught. So this is how the equation of the graph will look like, right? Okay. For example, let's do an example. For example, so the example that I have in mind, let me look at the notes, is the following. So find, because I want to use something similar, so it's a similar function, find an equation for the tangent line to the graph of f of x equals 1 over x at the point where x equals 2. Okay. So clearly we have to compute the derivative. So let's do that. And then we'll plug in, we'll see, we will evaluate the derivative at the point x equals 2. So the derivative of this, so we have to compute the derivative right? The derivative of f of x equals 1 over x. So we have to compute the derivative of this guy. So now what we have to do is to, well, I can say what the derivative is, but you can use the difference quotient. And in fact, let's do the computations. So f prime of x is nothing else than just the limit as delta x approaches 0 of f of x plus delta x minus f of x, everything over delta x, right? So that's the definition. And now this will be equal to the limit as delta x approaches 0 of 1 over x plus delta x minus 1 over x over delta x. And now let's do the computations here. So this would be equal to the limit as delta x approaches 0 of x minus delta x. Okay, I'm just gonna do it directly. It's just x times x plus delta x times delta x, right? So this would give us nothing else than just the limit as delta x approaches 0 of -1 over x times x plus delta x. And well, now you can look at this guy. As this guy approaches 0, this will give us nothing else than just -1 over x squared. Well, that's the derivative. So f prime of x is -1 over x squared. Okay, beautiful. Now the only thing we need to do at this point is to evaluate. So we need to evaluate the derivative at the point 2. So f prime of 2 is -1/4, and also f of 2, if we plug it in, is 1/2. Well, the equation of the tangent line, as you can see here, I can write it explicitly. So the equation of the tangent line is given by, well, y will be, and if we look at the formula, so it's f prime at 2 times x minus 2, right, plus f of 2. Well, we know these values, so this will be nothing else than just -1/4 times x minus 2 plus 1/2. Anyway, you can do the computations, and that's it. So this is the equation of the tangent line. Okay, now in the remaining time, I would like to say a few words what happens to the derivative of the function. And when the first derivative is positive, when the first derivative is negative, or when the first derivative is 0. And then also I'll do some examples, and then probably after this we will stop. Maybe I should mention also how differentiability is related to continuity. So how differentiability is related to what we learned in a previous chapter. So now let me talk about the relationship between the graphs of f and f prime. So we would like to see how the graphs of these two functions are related. Okay, so the slope of f, right, is measured by the derivative. So we know this. And now we have three things that we need to know. If the derivative is positive, then we can say that the tangent line must be titled upward. must be tilted upward, right? So in other words, say the graph is rising. Or we can actually say something even better. The function is actually increasing, but anyway. Now, as you can imagine, the situation when the first derivative is negative, this will imply that the tangent line must be tilted downward. So this means that the graph is falling. Now the third scenario is when f prime of x is 0. So this means that the tangent line is a horizontal line, is horizontal at the point at x. So in other words, we can say that the graph flattens. Let's just say, write it like this. So the graph will flattens. Okay, so these are the three scenarios how the derivative, in which the derivative is related to the function. And in fact, I want to make myself even clearer than this, and let me just draw a picture so that you can see all these three scenarios graphically. All right, let's see here. Let's just say we have something like this, a function that is like this, right? As you can see on this portion here, look at it, on this portion here, f prime is greater than 0. On this portion here, if you want to look, f prime of x is 0. And if I want to go on this portion here, right, the graph of this is negative actually. So we see the three cases on this picture. All right, now let's just say a few words about the existence of derivatives. Existence of derivatives. Okay. So we can say the following. So a function is differentiable only if the limit, in the definition of the derivative exists. So this exists. Also, we can say that at the points where a function f is not differentiable, we say that the derivative of f does not exist. And now let's let's see 3 common ways for a derivative to fail to exist. So let me just draw 3 pictures. So 3 common ways for a derivative to fail to exist. All right, so let me just draw a picture so that you can see. Okay, I think I have enough space here. So I have a point here, C. Right, this is what we will call quarter point. Right, and we have another scenario. I think I can draw it here. We have something like we're going to have this point C here, and the graph will be something like this. Right, so here a vertical tangent, where is, and the third scenario, when so this is undefined here. So, and the third scenario is when we have something like this. So this is the point C. Now have here, so it will go something like this, the graph, and let's just say here will be something like this. So this is what we call point of discontinuity. Discontinuity. Okay, so this is the 3 common ways for which derivative does not exist. And in fact, let me give you an example now. And then, all right, let me give you an example. Show that, this is a very classical example, show that the function, let's just say f of x equals the absolute value of x, is not differentiable at x equals 0. All right, so let's look at this example. So in other words, we need to test the derivative at 0 to see what's going on. So keep in mind that f, so we know that the derivative of f is nothing else than just the limit of the difference quotient. Okay. Minus f of x, everything over delta x. So that's what we know. And now we would like to examine the derivative at the point x equals 0. So the derivative at x equals 0 is given by f prime of 0 will be nothing else than just the limit as delta x approaches 0 of f of 0 plus delta x minus f of 0 over delta x. And now this will be equal to the limit of delta x approaches 0 of 0, the absolute value of 0 plus delta x minus the absolute value of 0, everything over delta x, right? Or this will be nothing else than just the limit as delta x approaches 0 of the absolute value of delta x over delta x. And now what we have to do is just to use the definition of the absolute value of the absolute value. Keep in mind that the absolute value of delta x is plus delta x, positive delta x if delta x is positive, and let's include 0 as well, and negative delta x if delta x is negative. And now, guess what? We will have to take the left-hand limit and the right-hand limit, and you'll see that the derivative from the left and the derivative from the right, these two limits, in other words, will not coincide. So we can say that the derivative, the limit does not exist, and therefore the derivative will not exist at the point x equals 0. So let's see that. So now we take the lim as delta x approaches 0 from the left. Keep that in mind. We have seen what this means of delta x, an absolute value of delta x over delta x, which will give us negative delta x. Okay, which is the lim as delta x approaches 0 of negative delta x over delta x, which is negative 1. And also the lim as delta x approaches 0 from the right of the absolute value of delta x over delta x. This will be nothing else than just the lim as delta x approaches 0 from the right of plus delta x over delta x, which is 1. These two are not equal, so therefore the limit does not exist. And so we can say that the derivative of f does not exist at x equals 0. So this is an example of a function which is not differentiable at 0. So not all functions are differentiable at 0. All right, now there is one theorem that I would like to mention, and probably I'm just gonna stop after this. Maybe I'll just tell you a bit about the notations of the derivatives and so on. So I would like to address this issue of how is continuity related to differentiability. And we have the following theorem, which says the following. If a function f is differentiable at, let's say, at the point x0, then f is continuous at x0. So in other words, differentiability implies continuity, but not the other way around. So this is how they are related. Well, let me just, well, I mentioned with the notation, so let me mention one more thing about the notation for the derivative. Sometimes, you know, we denote this f prime, but physicists always like to do it with df over dx. So the derivative, so we can say that we can denote the derivative of y equals f of x, right, of our function y, by, we can write this in this way, dy over dx if we want, instead of f prime of x. Well, usually this is the notation used by physicists. Well, it started with Leibniz a long time ago. And we can say that the value of the derivative at the point, let's say x naught, is, we can write it in this way, dy over dx at the point x equals x naught. So this is how we can write the value in this way, right? And I will leave it to you as an example. There's one example in my notes if we look at it, and I'll leave this to you to do it. So example, so we're using this notation, we find dy over dx at the point x equals -1 if y equals x cubed. Right, you need, basically says find the derivative, in other words, of the function x cubed at the point x equals -1. It's the same thing. So again, you can use the difference quotient and so on. Okay, I think I'm gonna stop here. Thank you very much. Probably next time I will go and talk about the rules of differentiation. You will see how we apply some of the rules, how to find the derivative of elementary functions and so on. All right, thank you very much.